Are you seeing something?
Yes.
It's okay. Okay, so yes, this week I'm going to talk about another alternative method, and I think that the underlying idea is quite the same. And so it's based on some papers from the Scuderia group, and in one of his papers, he says that the idea is that with coupled cluster, you can always work harder and add higher excitation, and you will reach full CI and so the exact solution. But we don't really want to work harder because it's too computationally expensive. And so instead, it could be good to work smarter and to identify the the terms in the equation that are causing the problem in our single reference coupled cluster. And if we are able to remove those problematic terms, we could have a method which is working, but with an affordable computational cost. So last week uh, I show you the distinguishable cluster where we removed the two diagrams based on a physical argument. And so here it's more based on the class of term of the CCD equation. So here there is all the terms of the algebraic coupled cluster double equation. And based on the type of contraction that you have in your terms, you can sort them in 5 classes. So driver, ladder. So in the ladder, so the particle, so the contraction is particle, particle, or all. So the dummy indices are like CD in the double bar integral and CD here. Oh, can you see my pointer? I don't know how to say it.
Yes.
Oh, okay. So here it's so a part. Yes. Sorry. All contraction, and here it's a no. Here it's a particle particle contraction, and here all contraction. So that's the ladder term. When you have a particle all contraction, it's the ring term, and you also need to add the clustering term, which have also a particle all contraction, but with crust terms, and you need to add those terms to ensure the antisymmetry of your wave function. And finally, there is the mosaic terms with one particle particle or all contraction and one particle all contraction. So that's all.
So mosaic is a crossing between ladder and ring.
Yes. So, and because we have one particle particle contraction and one particle all contraction, there is only quadratic terms because you need two contraction to create a mosaic terms. So we can see what happened when we just take one of these class of terms. So here we always take the driver, and we see that, and we change the other class of term. So it has been shown, and it has been observed since 1977, sorry, that the ring coupled cluster method agrees with the RPA, so random phase approximation. So yeah, there is a lot of type of RPA, but I will be more precise in a few slides on which type of RPA. But so they have seen that there is this numerical evidence, and so it has been proved numerically then that with just those terms you have the same result as with the standard RPA calculation. And so the proof has been formally done by Scusaria et al. So in this paper,
Excuse me, Antoine.
yes.
Yeah. Can you say agree? I mean, this is exactly the same equations or not?
So that's the same result.
You say the same result, equivalence, but it's a lousy for me. Are there is there? I mean, the equations are the same or not between RPA and RCCD?
So in those two papers, they use the equation from RPA and the equation from ring coupled cluster double, and they see that the numerical results are the same. And later, Scusaria proved that the equation are equivalent, and so they are the same.
The same. So equivalence
Yes.
is always the same. Okay.
Yes. So just in those two reference, they just prove it numerically, and in this paper
Okay.
from 2008, Scusaria proved it
Okay.
analytically. And so, yeah, here I use the RPAX terms, but Scusaria just name it RPA, but this is easier to see which term are in the RPA if we call it like that. So yeah, so he proved the equivalence in this paper. So what is the RPA? So all the notation are from this paper from Anjan, and they say they give all the equation, and it's really clear. And so that's why I use their acronym and their notation. So like the RPAX. So if you start from the adiabatic connection, so you get an expression for the correlation energy. And so you are able to derive what is called the Plasmon formula. So that's the standard RPA formula. And so there is possibilities. So here it's a Coulomb integral, but you could choose a double bar integral, so with exchange. And here it's your density matrix, and you can choose the density matrix with exchange or not. So what Scusaria called RPA in his paper is the RPA. So it's the approximation with exchange in this term and exchange in this term. And what he called so direct RPA is the Coulomb integral here and the Coulomb integral here. And so in the paper from Anjan, they also look at the two other possibilities. So exchange here, but not here, and no exchange here, but not here. But for the coupled cluster, it's not, so I will not be interested in those two possibilities for the moment. And so, yes, that's the way we do our RPA calculation. And we can, sorry. And so that's the classical derivation for chemists, but there is another derivation, so which Scusaria used to prove the equivalence. So here it's our fermionic Hamiltonian, so the usual one. And you can do the approximation that your particle Hall excitation are bosons. So that's not true because they are not, those two excitations are not commuting. That's not the real algebra, but you can just see what you get if you say that particle Hall excitation are bosons. So yeah, so here are the usual bosonic commutation relation for our new operator, and you can re-express your fermionic Hamiltonian in terms of those new operators. So you bosonize this operator and you get this new Hamiltonian in terms of your bosonic particle Hall excitation. And so I've not put all the equation, but with this formula, you can diagonalize this matrix with a Bogoliubov transformation. And you see that you get the RPA the RPA yeah, placement formula. So that's the same. In fact, that's the same approximation that that's not the same approximation, but how to say it? Yes, it's the same thing. Just the derivation is not the same, but the underlying approximation in those two calculations. So the one presented by Engine and the one presented by Scusaria, that's exactly the same, but not derived in the same manner. And so they prove that if you put so this equation in a matrix form, you can show that it is exactly the same method. And so they proved what has only been numerically observed before. And in RPA, there is another possibilities is to not use particle Hall excitation, but you can use particle-particle excitation and do the same things. So you bosonize your Hamiltonian, but with particle-particle excitation, and you will get what is called a particle-particle RPA. And in fact, it is known that when the particle Hall RPA is unstable, it is due to an instability of the Hartree-Fock reference, which becomes another Hartree-Fock reference. So there is an instability in the particle Hall RPA. And for the particle-particle RPA, when there is an instability of the reference, it is known that the instability gives us another reference, but a number of symmetry broken number of particles. So those two types of RPA don't have the same instability. And in fact, Scusaria did the derivation with general quasi-boson excitation. So he says that you have quasi-boson which are particle Hall and also particle-particle excitation. So he did the analytic derivation with all the possible excitation, and so doing this, he can prove all the equivalence in just one derivation. And so the other equivalence, yes, sorry, I forgot to mention it for the moment, but if you take just the ladder term, you get the particle-particle RPA that I was talking about. And yeah, so we see that there is those terms in the couple cluster which are equivalent to a formulation of RPA, and the same thing for the ring couple cluster, which are equivalent to another formulation of RPA. And so we can think that if we know that the RPA is unstable in a case, we can just remove the term linked to this formulation of RPA in our couple cluster calculation, and think that it will remove the problem in our couple cluster calculation. So yeah, just to see the proof of the concept, so we can look at those two curves. So from a paper from Bulik, Anderson, and Scusaria. And so on the left, this is the dissociation of the nitrogen molecule in the STO3G basis set, so a minimal basis set. And we can see that the couple cluster double fails to describe the dissociation, and the particle Hall RPA is really bad at every bond length. But if we remove the ring, and we also remove the crust ring terms to ensure the asymmetry. But so yes, it's not a really good result, but it's qualitatively correct. So we see that by removing those terms which are linked to the instability of the RPA calculation, we can remove a part of the problem. Yes, of course, it's not. Yes, it's just a proof of concept. It's not quantitatively usable. And so the other example is for the pairing Hamiltonian. So as a function of the interaction strength G. And we can see that this time the particle-particle RPA is unstable. So they tried to remove the ladder term because they are the ones equivalent to the particle-particle RPA. And once again, we see that it's quantitatively better than couple cluster doubles. Qualitatively, sorry, but not quantitative. So yes, that's just a proof of concept that by removing terms, we can get a better result. And so for the moment, I have not talked about the Mosaic terms. So we know that for example, in the homogeneous electron gas, ladder coupled cluster double and ring coupled cluster double are divergent because the gap between the HOMO and the LUMO is closing in the thermodynamic limit. And when we add the Mosaic terms, this divergence is eliminated. And in fact, it's because those terms are renormalizing the one electron energy because those Mosaic terms are present in the one electron effective Bruckner Hamiltonian. So yeah, at each step of your calculation, you renormalize your energy. And so those Mosaic terms prevent the gap to close in the thermodynamic limit. So yes, and that's my last slide. I hope it was clear.
Sorry, I was muted. Yes, thank you.